Well, let's continue on with our discussion about slopes and lines. We've been looking at functions and ski hills even, and talking about the slopes that come up there. We represent this with a line. So Matt, I think it's really important for us to talk about the equation for a line.
Oh, I see you've got something that looks like the equation for the line in the graph.
That's right here.
Y equals mx. And there's also an orange line at the bottom. Is that the line for m equal to 0?
That's a line with slope exactly 0. So y is equal to 0 times x, which means the y value is just constant 0.
So let's look at a bunch of fan lines coming out, see what it looks like for different values of m.
So for this equation, y is equal to mx. X and y are variables, so all we're going to do is change the different slopes. So if we get different slopes, we get different lines.
So we can go from a slope of 0 to a really big slope, maybe even an infinite slope if we're right on the y-axis.
That's right, although usually in these equations we don't let m equal infinity, but it might be a million.
Very steep. Now, that's kind of a bit restrictive because we have the fan of lines all emitting, if you like, from or going through the origin. Let's see what we can do about moving the fan around. So let's change the fan to sit at a different position in x, but keep y equal to 0.
So to allow for that, we need to change this origin to a point x naught, y naught. So let me change the equation. So now, okay, the equation doesn't look like it changed because I'm just subtracting zeros. But now I can change this 0. There's 2 zeros. Change one of them to an x value and the other one to a y value. So which one should I change first?
So change the x and leave the y value to 0. So the fan is just going to move along the x-axis. There it goes. And you see the numbers are changing.
See, now I'm at the point 1, 1 for x, and I have x minus x1. X minus 1.1. Let's move it even a little further along.
Oh, that's a good place.
Okay.
Now, that's also too restrictive. I want the fan to be anywhere in the xy plane, so let's move it up at that x and move it up in y.
So I move it up, and we notice the other 0 changes. And so here, the y value, y naught is 2. And I get this equation. Y minus 2 is the slope times x minus 4.
Now, can we use this idea of these fans and attach them to a smooth curve?
You read my mind, Matt. So I have a nice smooth curve that passes through this point. And let me show you that curve. Oh my gosh, it's a parabola again.
Oh, that's amazing. And we can even see one of those lines is really close to being right, the nice slope attachment to it. Maybe you can zoom in, or what can we do?
Let's do this. Maybe we can remove a few of these lines. Obviously, this line here is too steep, so we can get rid of it.
That's too steep. Get rid of that.
Oh, that's not the one I want to get rid of. I'll get rid of a few of them. Got rid of that one. The next one, it also looks too steep. This one maybe is a little too steep. That one looks pretty good.
Yeah, that top one looks really quite good.
The bottom ones are not steep enough, so we can get rid of them.
And that one does a very good job of touching the curve at the point that you can see.
So there we've got a line. It's got a particular slope. It's going through a point on the curve, and that's our best approximation to the curve using this formula. Y minus 2 is equal to m times x minus 4.
So m is an unknown constant, its slope, and it changes, though, as we go along the parabola, because it's a function of where we are in the parabola. And then also, as we move along it, the 2 will become something else, and the 4 will become something else. Do you happen to have a formula handy?
Not in this video, but why don't we try that next time?
I'm looking forward to that.
Sounds great, Matt.